Welcome back to Stewart Science. Today we're getting to the end of our constant velocity motion unit. So we're getting to the end here and we're saying, what has all this hard work been about? We've represented our motion with a diagram, we've represented it with words, we've represented it with two different kinds of graphs, and now we ask the question, what can we do with all of this information? And the answer to that question is, we can use the model that we made to make concrete predictions about where the car will be at certain times or how much time it will take the car to get to certain places. So we've gotten this relationship between position and time. We've put it on a graph, we've gotten a slope, and we've distilled it down into a y equals mx plus b. So if you haven't watched it yet, go back and watch those videos because I showed us how to get to this point. We have a graph, we have all of this really important information, and these two bits of information right here, the slope and the y-intercept, can let us make predictions about where this car will be at any point in time or what time it takes us to get to any point in space. So we start with that equation, y equals 8x plus 15 for that graph. And the 8 was our velocity and the 15 is our starting point. So the 8 is how fast the car is moving, the 15 is where it starts, and so we know that its position equals 8 times its time plus 15. That was all that hard work. So if I give you a random time, let's say I give you 22 seconds, and I ask, where is the car at 22 seconds? Well, seconds, time, is on our x-axis and positions on our y. So if I give you a time, you need to plug it into your equation where the x is. So you plug it in for x, and so now our equation is going to look like this. Position, which is our y, equals 8 times 22 plus 15. After that, it's just an easy numbers game. 8 times 22 is 176 plus 15 is 191. That is a good number. It's not a good answer because it needs a unit. That unit is centimeters. Ta-da! So all I did was I gave you a time, which we put in for our x, because time is on our x-axis. Then we just ran some numbers there, got out our calculators, did some typing, boom, gave us a good prediction, 191 centimeters. Now we can do it the other way too. So let's say I give you a position and then I ask you, how much time did it take us to get there? So I'll use the next example from that other video, which was this. And my face is covering up some of the information, but you can still see the stuff we need, which is the m is 6 and the b is 100. So this graph has a y equals negative 6x plus 100. Which means that its position is negative 6 times the time plus 100. That's what our graph gave us. So now if I give you a position, you can figure out how much time it took to get there. So let's say I gave you a position of 0. I want to know, if I'm the observer, how much time do I have before this car runs into me? I plug in 0 where the y is, because on that graph, the y-axis is the position. So I put that where y is. So I have 0 equals negative 6x plus 100. At that point, it's a little bit trickier because I have to do just a little tiny bit of algebra. So I need to get the x by itself. To do that, I start by taking away 100 from both sides. And that's going to give me negative 100 equals negative 6x. All I did was subtract 100 from both sides to get rid of that 100 from the right side. Then, to get the negative 6 off, I divide both sides by negative 6. And that's going to leave my x alone. Negative 100 divided by negative 6 equals 16.67. And again, that's a good number, but it's not an answer until it has a unit, seconds. And that equals our time, which is on our x-axis. So if I give you the information on the x-axis, all you have to do is plug it in for x and then grab a calculator. If I give you the information on the y-axis, you have to plug that number in for the y in the equation and then do just a little bit of basic algebra and then go to your calculator in the process. So I'll give you two more examples. Here's another example from what we did in the other video. We got a slope for this data of 15 and a y-intercept, so a starting point of 250. Velocity of 15 centimeters per second, starting point of 250 centimeters. So again, if I'm looking for a position and I know the time, I put the time in for the x because time is on our x-axis. When I do that, I get y equals 15, which is our velocity, times 53, which is our time, plus 250. At that point, it's just a numbers game. 15 times 53 is 795 plus 250. 1045. 1045, need a unit, centimeters. That easy. If I give you information on the x, you plug it in for x, go to town on the numbers. One more example for the y. Here's a graph that we did in that last video. Our slope is negative 15 centimeters per second. Our starting point is 1,500 centimeters. And so I had this equation, y equals negative 25x plus 1,500, which means our position is negative 25 times our time plus 15. So if I give you a position, let's say 50 centimeters, I put that information in for y because the position is on our y-axis. So I would have 50 equals negative 25x plus 1,500. At this point, it's just a little bit of algebra. Take away 1,500 from both sides, do a little subtraction first. And when I do that, I've got 1450 equals negative 25x. Then divide both sides by negative 25 to get x by itself. And I get 58 equals x. Need a unit? 58 seconds equals time. So if I give you information for the x, you plug it in, grab a calculator. If I give you information for the y, you plug that in for the y, and then you do a little bit of algebra, calculating as you go. So here's the general overall conclusion here, where we went with this. We all know y equals mx plus b, the slope and the y-intercept, the m and the b. In this case, that m is the velocity, and that b is the starting point. So we know y equals velocity times x plus the starting point. Those are numbers. Velocity and starting point are numbers that LogRPro or graphical analysis gives us. Now on the y is our variable for the y-axis, which in our case is position, and on the x is our variable for the x-axis, which is time. So we can replace the y and the x too. Position equals velocity times time plus starting point. Now, because we're scientists, we're lazy, we don't want to write out the whole word. I don't want to write the word position every time I'm doing an equation. So I use a variable, which is just a letter, to represent position. And I know this is confusing. If I were to go back in time, I'd punch whoever did this in the face. But x is what we've chosen for some reason to stand for position, which I know that's confusing because in our graph, it's on the y. But x means position, which is on the y-axis. I know it's confusing. I'm sorry. I didn't do that. That wasn't me. But that's what you're going to see in a textbook. So x equals, and then instead of using the whole word velocity, I'm lazy. I'm just going to write v instead. Instead of writing the whole word time, I'm going to write t. V, velocity, t, time. Those make sense. The starting point would be x with a little 0 in the corner. Again, sorry. I didn't do it. The physicist did it. But X is the only one that's really actually confusing. X stands for position, which in our case was on our y-axis. I know, it's confusing. But what we get from this is X equals V times T. Should be a little times sign in there. I don't know why it didn't show up. Which if we rearrange using algebra, we get V equals delta X divided by T. And that's the equation that you're going to see in every science textbook or every class forever. If you think about it, it makes sense. If I'm going to say I'm driving 70 miles per hour, that means that I will cover 70 miles per 1 hour. We use this stuff without even thinking about it, but now we know why. So that's where we went with this. If I know a velocity, you can plug it into that equation, and all I need to know is position or time. I can find the other one. It's really simple, plugging in numbers. I actually like to use this equation, delta x equals v times t, because the algebra is very easy for that one. You never have to worry about screwing something up. So that's our conclusion. Delta x, which is change in position, equals velocity times time. I'm Mr. Stewart. As always, keep learning no matter what.